This is our second tutorial on phasors. In this circuit, we are given the voltage applied to the circuit, a sinusoidal voltage of 100 volts RMS and 500 radians per second as an angular frequency omega. We apply that voltage and the total current resulting is also known as 2.5 amps with the same angular frequency. Both have 0 degrees of phase shift. So we know this voltage and this current. This resistor is 20 ohms. This capacitor is 100 microfarads. We are to compute the inductance in henries of this inductor in this branch. Let's proceed. The first step is to represent all voltages and currents by phasors. And this is easy. The voltage in this case is represented by phasor, an IEEE phasor, an RMS phasor, with a value of 100 volts, the RMS value, and the phase, in this case, of 0 degrees. So I could write this just as a real number, 100 volts. And the phasor for the total current is, in this case, 2.5, with a phase of 0 degrees as well. Another real number, 2.5 amps. The second step is to represent all the passive elements by their impedances. 20 ohms remain 20 ohms of resistance, but the capacitance is represented by its impedance. Negative J 1 over omega C, who is omega, the angular frequency of the sources, 500 radians per second, multiplied by the capacitance, which is 100 microfarads. Allow me to write, instead of 10 to the negative 6, I write 10 to the 6 on the numerator. That impedance is negative J 20 ohms, the impedance of this capacitor. Well, the impedance of the inductor is, of course, J omega L. We know omega is 500. We are to compute what is L. We know what is the voltage across this inductor is 100 volts RMS, but we do not know the current in the inductor, this current. If we did, we could just divide the voltage by this current and obtain this impedance and divide by J omega and find what is the inductance, L, of course. But let's see how we can compute this current IL. We know the current IT. We can compute this current. Let's call that I2. I2 is just the total voltage from here to there, which is just V, 100 volts, divided by the impedance of this branch, 20 negative J20. That current, I2, is no other than the voltage 100 divided by the impedance of that branch, 20 negative J20, and for that we use our calculator. 100, enter, round parenthesis, 20 space, 20 change sign, divide. And that is a current, I2, but in rectangular form. In polar form, that is a current of 3.536 amps with a phase of 45 degrees. Now that we know that, we can compute the current in the inductor using KCL. It's just the total current, 2.5, this one, minus the current I2. That's how we compute this current. Minus this current that we just computed a moment ago. Again, we go to the calculator. 2.5, enter. Swap, subtract. That is the current in the inductor. 2.5 amps with negative 90 degrees. And we are ready to use Ohm's law to determine first the impedance of this inductor, and then we will divide by J omega to obtain the inductance. The impedance of that inductor is the voltage across, which is 100, divided by the current through the inductor, 2.5, with negative 90 degrees. We go to the calculator. 100, enter, swap, divide. That is the impedance of that inductor, 40 ohms with 90 degrees. 40 ohms with 90 degrees. In other words, it's J40 ohms. but that is j omega L. From there, dividing by j omega, we obtain what is L. We say the inductance L is just that impedance divided by j omega, which is j 500. We go again to the calculator. That impedance divided by round parenthesis 0 space 500 divide. That is the inductance, a real number with a value of 0.08. 0.08 henries. That is, the inductor has an inductance of 80 millihenries, and that is the solution to this problem. Thank you very much.